Great to see you here again. My name is Luc de Ceuster, founder of the Ceuster Academy, and welcome to our new YouTube video about linear congruences with one solution. But before we start, do not forget to click the subscribe button, click the bell button, so every time we have a new video, you will be informed about it. Let's go to resolving linear congruences, and we've seen in previous videos how we can deal with it, what are the strategies to follow, and we looked at different solutions. In this specific video, we will be looking into linear congruences that have one unique solution, modulus n. And the linear congruence that we are going to look at is 117x, which is congruent with 59 modulus 451. The first thing what we have to do is to calculate the GCD between 117 and 451. What will be this GCD? We know that in order to have a unique solution modulus m, this GCD has to be equal to 1, and then we can calculate with the Bezout coefficients, we can find the modular inverse of a modulus m, or 117 modulus 451, and then we can in fact find the solution. So let's start with the Euclid algorithm. First we can say that 451 can be written as 3 times 117 plus 100. Now you can stop the video here and do the calculations yourself and continue and see how this works out. But let's continue from here. So we go 117 is 1 times 100 plus 17. Now we take 100. We can write this as 5 times 17 plus 15. 17 is 1 times 15 plus 2. 15 is 7 times 2 plus 1, and 2 is 2 times 1 plus 0. So we find that the GCD equals 1. So basically from this we know that there is one unique solution, modulus m. Now we have to find the Bezout coefficients, and the Bezout coefficients we start by doing what we call the inverse or the backward path. So we start by writing 1 is equal to 15 minus 7 times 2. So that's the first one equation that we start from. And now we can introduce the second equation. We write it as a function of 2. So we have the second equation, which is 2 is equal to 17 minus 1 times 15, and we bring it in this equation here. So I find 15 minus 7 times, and I replace the 2 by its expression 17 minus 1 times 15, which is basically, we have 7 times 15 plus, of course, minus 7 times minus 1 is 7 times 15 plus 1 is 8 times 15 minus 7 times 17. The next step, we take equation 3. Again, we express equation 3 now in function as 15, and we can say 15 is 100 minus 5 times 17. And we bring that in the equation, and I will immediately give you the result here. So we put the 15 here, and what we find here is 8 times 100 minus 47 times 17, and I'm peeking at the board in front of me, which gives me the solutions, of course. Now we have the fourth expression. This was the third one. So now we have the fourth expression, which is in fact 17 is equal to 117 minus 1 times 100, and we can write the GCD 1 again as a new relationship by putting the 17 in here. So we have basically here, we find 55 times 100 minus 47 times 117. And in the last one, we have the fifth equation here. So in the fifth equation, we have 100 is equal to 451 minus 3 times 117. And the final result that we have here is 55 times 451 minus 212 times 117. Now what we find here is that the term S in the equation is equal to minus 212, but when we use the modulus 451, we can say that the modular inverse is equal to 239. The remaining thing to do is to input this in the equation. So where can we put it? I have some space left here. Which color? Orange, yes. So what we can do now is say that we multiply both sides by 239. So we multiply this by 239, and basically we find here 239 times 117x. So we have basically here 239 times 117, and in the modular arithmetic this is equal to 1. And the other element we find 59 times 239. When we put this in the modular arithmetic, we find that this is equal to 305. So basically, based on this, we can say that we have x is congruent with 305 modulus 451. And basically, that's the final solution of this linear congruence. Basically simple, GCD, we have to prove that it's equal to 1. We do that using the Euclid algorithm. Then we find the Bezout coefficients by doing the backward pass. We found the negative coefficient here, but we like the positive ones. But with modulus 451, we can find that this is equivalent to 239. We multiply the expression by 239, and what we know, because 239 is the modular inverse of 117 modulus 451, we know that in the modular space, the product of 239 and 117 is equal to 1. Then we have 59 times 239. When we bring that to the modular space, when we look at this modulus 451, we can find that this is 305, and basically we can write the solution as x is congruent with 305 modulus 451, which is basically the solution. But let's do that again with a second exercise so you really understand the subject. Let's have another exercise here. Now we're going to look at the linear congruence. 109x is congruent with 13 modulus 32. We're looking into solutions, unique solutions. Does this congruence have a unique solution? Well, we know that there is a unique solution when the GCD of 109 and 132 is equal to 1. And this is so because the simple fact 109 is a prime number. So that's in fact immediate proof. Now what we want to do, of course, we have to find the Bezout coefficients. We can use a different solution. We can use the classical approach, but let's do it with the Bezout coefficients. So we can say that 132, wrong color, black is better, 132 is 1 times 109 plus 23. Now we continue with 109 and 23. 109 is equal to 4 times 23 plus 17. And now we have 23 is 1 times 17 plus 6. We have 17 is 2 times 6 plus, it's 12 plus 5. And now we have 6 is 1 times 5 plus 1. And we find 5 is 5 times 1 plus 1 plus 0. So this is the GCD. And we start with the backward pass from here. So how do we do the backward pass? So we start from the equation 1 is equal to 6 minus 1 times 5. We put the equivalent here, we replace 5. We take 5 equal to 17 minus 2 times 6. And we find, you can calculate this, that this is 3 times 6 minus 17. Now we continue with the next equation. We can say that 6 is equal to 23 minus 17. When we replace it here, we find that we have 3 times 23 minus 4 times 17. We continue, and now we have 17. 17 is equal to 109 minus 4 times 23. And we find again, 1 is, in this case, 19 times 23 minus 4 times 109. And the last adjustment, we have to replace 23, which is 132 minus 109. And we find that 1 is equal to 19 times 132 minus 23 times 109. So what we find here is that S is equal to, S is minus 23. So when we find the positive equivalent modulus 132, we find that it's 109. And when we're going back to the equation, we can now put that in the equation, and we can say we multiply both sides by 109. So I find 109 times 109x is congruent with 109 times 13 modulus 132. This side is equal to 1, and we know 109 times 13, that's 1417. When we look at all of that modulus 132, I can say that x is congruent with 97 modulus 132, which is the solution for this linear congruence. It's also possible to use the definition of the congruence to find this. We can say that 132 divides 109x minus 13. And you know that we could write here that 109x is equal to 132 times k plus 13, and we find for k is an element of z plus. Excuse me. So we could find the value for x that complies with this equation. But we use the Bezout coefficients. We have different ways to do it. The most important thing is that you know how to find that this linear congruence has a unique solution, modulus 132, and that's what I wanted to show you. But we have more exercises in other videos. Do not forget to look at the text below the video. There are links to our different courses on our website, theceusteracademy.com, and of course there are nice coupons there, coupons that give you a great discount when you subscribe or buy our courses. Anyway, this is the end of the video for YouTube, so don't forget to click the subscribe button if you didn't do that yet, and click the bell button so every time there is a new video offered to you by the Ceuster Academy, you will know about it. Thank you very much and bye-bye.